Hello and welcome to this video. In this video and the next couple of videos, we'll talk about counters. So in this video, we'll start out by just talking about flip-flops, and we'll talk about flip-flops. So the way I'll run through the next couple of videos is we'll first talk in the digital domain, just talking like let's say we're working with flip-flops, and then we'll go on to VHDL and write the code in Quartus. The board I'll be using for the next couple of videos will be the DE10 Lite. So let's start with a flip-flop. The most popular flip-flop that we'll probably have out there is the DFlipFlop. And your DFlipFlop has two inputs and, well, two outputs. So the first input, the top input, is what we call our D input. The lower input is our clock. We typically will send in our clock into the lower input. Then we have two outputs, our Q and our Q bar. So these are typically the exact inverse of each other. So these are DFlipFlop. The characteristic of a DFlipFlop is that whenever an active clock transition comes in, then whatever is at your D input gets transferred to your Q output. Some parameters you want to think about are your hold time, your setup time, and propagation delay. We won't talk much about that in this video. Just suffice it to say that whenever an active clock transition comes in, the signal that was at D before that active clock transition comes in is the signal that gets transferred. So there is a setup time that the signal must be at D at least a certain amount of time before your active clock transition, and it must remain at D a certain amount of time after your active clock transition for that signal to be guaranteed to register as at D. Okay, so if we have a 1 at D and an active clock transition comes in, then 1 gets transferred to Q. No matter what Q was before, Q will definitely be 1 after my active clock transition. It might take a short while, which is called our propagation delay, for that input to get transferred to the outputs, but that's that. Okay, so that is our D flip-flop. There is another flip-flop that is based on this, and that's what we'll actually use in this video. Now, this is also a D flip-flop, but in this particular flip-flop, we take the inverted output and we send that back to our D input. So this which would have been which is our D input gets its value from the inverted Q. So this is our Q bar. Q bar is what gets sent back to our D, and that's our regular Q output, and this is our clock. And one thing I should probably mention is because there is no bubble on this in this diagram, then the active clock transition will be a positive going transition. So when it's going positive, that's the transition that will clock this particular flip-flop. If I wanted it to be clocked by a negative going transition, what I would have done is I would draw the clock input with a bubble. So once you have a bubble at that input, then this will be clocked instead by the negative going transition of the clock. So once your clock is going from 1 to 0, that is what will clock this particular flip-flop. So that could be our D, our Q, and our Q bar. So here again, we're going to use our PGT. I'll just keep it as PGT. And so if we have a clock signal coming in here, our CLK, clock signal coming in here, our output will be taken from our Q. Okay, but take note that your Q bar gets routed back to D. If two wires are crossing each other and they're connecting, I'll put a dot. So if I wanted this to be connected, I'd have put this dot there. So just take note, that's how I draw the videos. If they are not connected, then I'll draw it this way. Well, maybe for clarity's sake, maybe I should draw a bridge so that it will be obvious they are not connected. Okay, so I'll try to remember to always draw it this way. In case I don't, look out for the dot to know things are connected. So this flip-flop in this arrangement is called a T flip-flop. T standing for toggle. Why is it called a toggle flip-flop? Whenever you have a 1 on Q, a 0 will be on Q bar. When you have a 0 on Q, 1 will be on Q bar. In other words, let's say the output at Q is 1, then the next input to your D will be a 0. So whenever an active clock transition comes in, 0 gets transmitted to Q. So we had 1 before at Q, 0 got transmitted. Next clock transition, you will have a 0. When you have a 0 at Q, that means you have a 1 at Q bar. So 1 is coming to the input D. Active clock transition, what we get out will be a 1. And then it will go on that way. So in other words, whenever there is an active clock transition, your output will flip from whatever it was before to the other value. So if it was a low before, it flips to a high. If it was a high before, it will flip to a low. So that is called toggling. Okay, so we'll say the output toggles from 0 to 1 or from 1 to 0. So this is a toggle flip-flop. What it does is that it always toggles. Whenever there's an active clock transition, it toggles. So this is our TFlipFlop. This is how it works. Let's go ahead and define this in Quartus. Now, I should probably mention that we do not need to define a TFlipFlop in Quartus. If you wanted to use a DFlipFlop or a TFlipFlop, just write your code on how you want to use it, and Quartus will interpret things. But for the sake of learning purposes, let's go ahead and define a TFlipFlop in Quartus. So new project. I'll save this in a folder that I call projects, and then I'll create a folder in there that I'll call, since this is a course on counters, I'll go ahead and call it counters. And all the projects I create, I'll put them inside this folder called counters. So this would be a TFlipFlop, so I'll simply call it TFF. Top level entity, I'll also let that be TFF. Let's go next. It's saying counters does not exist. Do I want to create it? Yes, please go ahead and create it. So it will create that. I'll just simply go next. I need to specify the FPGA that we're going to be using. Remember, we're using a DE10 Lite. Now, one thing you could do is you could come to these boards here and you could select the Max 10. But if you're going to select the Max 10, you need to know specifically which of the boards you are making use of. Okay. So, for instance, you have this board here, which is a DE10 Lite, but the particular FPGA on it is not exactly the one we are using. So instead, I'll come to device and just simply type. If you check the side of the device, you see what is written there, and I think it is a 10M50DAF484C7G. Okay, and so that is the particular device that we're going to be programming. I'll just leave this as is. I'll just go ahead and leave this as is, go next and finish. So that will create a new project, and in here we're going to specify our VHDL file. Project created, Control N. We're creating a new file, VHDL file. Okay. In here, I'm going to use library. Now, you're almost always going to use the IEEE library whenever you're creating your VHDL code. Okay. So this is the IEEE library. We're going to use IEEE.standard logic 1164.all. So let's create our entity. Remember, we said our top level entity will be TFF, so I need to specify it as TFF and I'll go ahead and just end entity TFF. In here, I'm going to specify the ports. Now let's come back to our diagram. How many ports does this have? Remember, this is our TFlipFlop. Because this output is wired directly to the input, we really just have only one input, which is your clock input. We don't write anything to D, it's automatically is written from Q bar. So all we simply have is one input, which is your clock, and we have one output, which is your Q. Okay, one output, which is your Q. So we can just specify that in here, that we're going to have one input and we're going to have one output. Okay, so there'll be a semicolon after that. So we're going to have one input. CLK will be my input, type will be standard logic, and the output will be my Q. So Q will be my output, and it will also be of type standard logic. Okay, so that's good. And next we need to define our architecture. Let's say architecture toggle of TFF is begin and architecture toggle. It's usually a good idea whenever you begin something, end it immediately and then now type in your code in between, so that way you never forget to put the code in between. So architecture toggle of TFF is, let's go ahead and specify how this toggles. Now what we have is a sequential circuit. Okay, so if you have the system working, nothing happens until you have a clock signal coming in. Nothing happens until a clock signal comes in. In other words, your output does not toggle until you have a clock signal coming in. So what we have is a process. The output at present, remains the output at present until a clock signal comes in, and then the output will flip to the other output. Okay, it will flip to the other value. If it's a high before it flips to a low. So this is a process because it is a sequential system. Okay, so we'll specify process. Sensitivity list in this case would just be clock, because the system is responding just to clock. Whenever clock changes, then the system responds. So process clock, begin and end process. We could have chosen to name this process. So let me name the process T1, and we do that. So we could end our process here. We could end process T1, but I'll just leave it as is here. Now, what we want to do is, we want, whenever there's an active clock transition, okay? So whenever there is a change in clock, this process will be called whenever there is a change in the clock. But then that change may be the clock going from 0 to positive, from 0 to 1, or going from 1 to 0. So there are two ways we could do this. We could say if CLK what's called single inverted commas event, and CLK and the value of CLK is 1. Okay, that is a high. We could say that, so this refers to a positive gain transition. So there was an event on clock and the value now is 1. So there was an event and the value is 1. That is a positive gain transition. But this is a lot of writing, and an easier way of typing this is simply saying rising edge of CLK. So as long as we have a rising edge of CLK, then we want to do what is next. So end if, just to make sure I don't forget to close that. So if rising edge of CLK, then what we want is our Q will now be not Q. And at this point, let me pause and talk about processes. How do processes run? Now, for sequential logic, remember that this is a process. Processes define sequential logic. In other words, the first line of code inside this process will run before this next line of code, before the next line of code. In this case, really, there's just, if you want, one line of code in there, which is dependent on the on this if statement. So if rising edge of clock, then Q will become not Q. If not rising edge of clock, it will never enter this loop, and it will just simply skip over and the process will exit. Now, I should mention that every assignment you have inside a process the assignments do not happen until you have this end process command. That is the point where all the assignments happen. So for example, if I had done something of this nature, 1, and then Q assign 0, I can do this inside the process. It is perfectly valid. This would not cause a conflict like you would have had if this were just outside the process. Now, if this were outside the process, this would be concurrent statements, and VHDL will have a problem. It will tell you that we cannot do this because we are assigning several different values to the same output, and that is not allowed. But in sequential logic, you can do this. However, if you run this piece of code, when this process ends, all you will see on your queue will be this last line of code, which is a low, because it runs through this line and then this line and then this line, but the assignments actually do happen at this point. The values will get written at your end process. So the value on Q will simply be 0. You will never see this not Q. You will never see this high. So just take note about that. So for this program, we actually do not need this. So I'll just take them off. Okay, so Q is equal to not Q, and we'll go ahead and save this as TFF. Okay, so we've saved our code as TFF. I'll run through analysis and synthesis. Let's just compile this, make sure that it compiles without any issues. Now, to test that this program actually works, the best thing to do will be to write a test bench. So within a test bench, you could supply clock signals to your clock input, and then you can now check to see that it is working well. Okay, so we have an error in here. Q mode cannot be read. Okay, yes, that's correct. So here I simply said that my Q is equal to not Q, but the problem is this: Q is an output. So how can this entity, so let me come back to this diagram that we have over here. Remember that in VHDL you have entities and you have architectures. Everything is an entity. Okay, so if we define our entity here, this entity here, we defined it with the name TFF. We said it has one input, which we called CLK, and we said it has one output that we called Q. Now, inside of it, I wrote some code and I said that Q, it should assign what it should write to this output should be not Q. Now, inside this code does not know not Q because it received an input called CLK, but it does not have any input called Q, so it cannot respond to this. I hope you get that. It cannot respond to this. So what we are going to need to do is that inside this entity, we're going to have to define a signal, define a wire if you want, define a wire that we can bring backwards and now say not of whatever is in that wire. And that is what we can now send to the output. So we need a wire in here, and that wires are called signals in VHDL. So I'm going to come back to my architecture and I'm going to say signal. And I usually like starting my signals with S. So generally, any variable I have that starts with an S is probably going to be a signal. So I'll say S and I'll call it S underscore Q. So now this is a signal and I'm choosing to call it SQ. You could call it you could call the signal anything you want. The type of this signal will be standard logic. Okay, so outside of this process, I'm going to okay, so let me do that a little later. So what I'm going to do now is I'm going to say that my S underscore Q on rising edge of the clock, S underscore Q will be equal to not S underscore Q. I always like to initialize my signals. This is not absolutely necessary, but I always like to initialize my signal. So let's just initialize that there to 0. So SQ is equal to not SQ. Now it won't have a problem with this because it can read a signal, it can read a wire. Wires are known by the entity. The entity itself, the wire is inside the entity, so it can read the entity. It can read to wires, it can write to wires. But this is not connected to my Q, so I need to connect my wire to my Q. So I'm going to, outside the process, I'm going to specify that it should assign whatever value is on the signal to my Q. I am doing this outside the process because this is a concurrent statement. At every point in time, SQ is to be connected to my Q. This should not only happen whenever the clock fires, whenever there's a change in clock. Whether there is a change in clock or not, my SQ is always being assigned to my Q. So it's a concurrent statement. So we define it outside the process. If we define it inside the process, will it run? It likely will run, but then that is a bad design. You want to design it outside the process. So I'll go ahead and save this and run this, and now hopefully this should run through with no errors. So while this is compiling, one more thing that we should talk about. In flip-flops, many times you have, okay, it's saying TFF is, top level TFF is undefined. Why is that? TFF is defined. Entity TFF is defined, TFF is defined. So what is it complaining about? So just give me a moment to check this. Oh, okay. So the problem is this: TFF exists, it is a primitive that exists in MATLAB, so we are not allowed to use TFF. So that means I'm going to have to use a different name entirely. Problem is, in my program, I have specified that my top level entity should be called TFF. So what I want to do is to change that name to my TFF. Okay. So I'm going to change the name to my TFF, and let's hope that this will now be happy with us. So I'm going to say my underscore TFF. Now I should probably edit all of this out of the video and not keep it in the video, but it's probably a good idea to leave it in there so that you see the kind of pitfalls that one could fall into and how to deal with them if one does encounter such issues or such errors. Okay, so right now it's running through, and this time there is no error in there. Good. So it has compiled and we're good to go. So we could test this by creating a test bench. But before I create a test bench, let me introduce something else. And this is the fact that with many flip-flops, you also have some other inputs which are called asynchronous inputs. Usually they are active low. So a low signal is what activates them. These are often called set and clear, or preset, set and reset. So I'll use the word clear because I like clear, and set. I'll use the words set and clear. So let's introduce this. What this does is whenever a low signal comes to set, your Q jumps to 1. No matter what was going on, Q goes to 1 as long as there is a low signal on set. With clear, whenever there is a low signal on clear, Q will go to 0 no matter what happens. So obviously you should never have the same signal going to set and clear. That should never happen, okay? Because that's about this, that will cause a conflict where to be wondering, should I set or should I clear? So let's come to our code and let's introduce those two asynchronous inputs. Now I'm calling them asynchronous inputs. In other words, whenever a set signal comes or a clear signal comes, we do not wait for a clock. We simply directly go ahead and set, or we clear. Whenever a set or a clear signal comes in, we don't wait for the clock. So if that is the case, then first of all, we need two more inputs, and our two inputs will be set and input standard logic, and we'll have another input called clear. Now, I'm concerned that set may not be available. I'm not sure whether it is available, so I'll just put I'll say n set, using n to refer to the fact that it's a, or let me say set n, because it is active low, so I used n there, and then CLRN again because it's active low. I'll just use that. Also, it's an input and it's standard logic. Okay, so here let's introduce that in here. Now we said that the set and clear signals will set or clear the outputs whether or not there is a clock. That is because they are asynchronous. So if that will happen, then it means in our sensitivity list we need to include set n and CLRN, because they should also trigger this process. Then let's come into the process, and what do we need to change in the process? On rising edge of the clock, this will still happen. Yes, that is true, but we need to specify something else. And what I'm going to do is this. I'm going to say that if a set signal comes, if set n is equal to 1, then my s underscore q will write a 1 to it. Sorry, this should be 0. Remember, it is active low. So if my set signal is 0, then this is this. Now, when you're writing your code, you need to take a decision which will be the first if that you place in here. By the way, let me just specify that this will now become an else if. I'm going to make the rising edge an else if. In other words, whenever this will take precedence over the else if. So if a set signal comes in, we will never enter this loop here. Okay, so this takes priority over your else if. Now, what we're going to do to make sure that it can never happen, that we have a set signal and a clear signal being active at the same time, we're going to use else if for set and clear, so that only one can be activated at any point in time. So what you will now need to decide is which you want to take priority, whether it is set or it is clear. So for instance, you could decide to have your clear n being equal to 0. You could decide to let that take priority. Many people actually would let that take priority, and then your else if, your set will now be an else if. Okay, so we have our s underscore q, we assign a 0 to that. So you could decide to let your clear take priority, and then after that, if there is no active clear signal, then we check if there's an active set signal. If there's no active set signal, then we now check whether there's a rising edge of the clock. Okay, let's go ahead and yes, save changes, yes please. So let's go ahead and compile this just to be sure that that runs, and then the next thing we now want to do is to test this system that we have developed, and I'll create a test bench for this system in the next video. So there we go, compilation has succeeded, and I'll go ahead and create a test bench for this system that we have created in the next video. Thank you.